so when I joined Bath, I was given this course, Metals and Alloys. So what I'm going to do is do the whole course in 5 minutes, yeah? So you've got to keep up, yeah? So all references from the web, yeah? So metals are metallically bonded, the clue is in the name. So what it looks like is free electrons with positive ion cores. So what they do is they pack very closely, close packed structures, a bit like snooker balls on a snooker table. Yeah, so you get very high density material. They pack very closely. Gold, 19, yeah? Aluminium's better, aerospace alloy, lower. So for example, this Australian couldn't carry the gold away. The atoms were packed so closely together. Michael Caine, Italian job, caused him problems. Lithium, 0.53. Remember that, I'll come to that at the end. So how do they pack in 3D space? This is body-centered cubic, this is iron. All you need to know is the atomium in Brussels is the BCC structures. It's the Belgian steel industry. That's an interesting fact to know. So face-centered cubic, gold, silver, copper, all deformable metals have that crystal structure. Hexagonal close packed, titanium, magnesium, important aerospace alloys. Now when you deform a metal, plastically, the planes of atoms slide across each other. That's easy. That's hard, yeah? So it's in the close packed plane and in the close packed direction, yeah? That's how you deform a metal. Now FCC, that has 12 slip systems, lots of ways for the atoms to slide over each other. Hexagonal close packed, only 3. So more brittle, less ductile. You can't deform it. So when I got married, I had a titanium wedding ring. I had a titanium, and the Julie said, we need to measure your finger size carefully. We can't enlarge it later. I said, of course. It's got a hexagonal close-packed structure. It's more brittle than FCC metals, like silver and gold. And the jeweller just looked at my wife with great pity. Now, metals are defective, yeah? This is a defect, it's a dislocation, it's an extra plane of atoms, just like I've got an extra row of corn on this cob. And when I deform it, I move these defects. They're mobile under stress. They weaken the material. So one analogy is it's a bit like a caterpillar. It's not very good, yeah? But the equally bad analogy, it's a bit like a rack in a carpet. It's easier to move that defect along, but it weakens the material. So, what happens if we stop dislocations from moving? What happens to the strength? It goes up. So we strengthen the metal. So how do you do that? Well, you use other defects. You alloy the metal and make it stronger. So how do you do that? So one example is to mix them on the atomic scale, copper and nickel. It's a bit like putting my ball in here. The main difference is the atoms are different sizes. So it strains the crystal structure. It impedes the dislocations. So this is a good example. Copper and nickel, pure copper 200, pure nickel 330. Mix them together, 400 and something. 430, yeah? It's stronger than the individual components. That's amazing. You've got to admit it. Now, the other way is to put in grain boundaries. They impede dislocations. They have to change direction. So if you make the grain sizes smaller, you have more grain boundaries and the metal gets stronger. That's why I like metals. Bigger doesn't mean better, yeah? Remember that. The other way is work hardening. As you deform it, it gets stronger. So what's happening is the dislocations are tangling up and impeding each other. So it's a bit like having 2 wrecks in your carpet. I don't know how you would do that in real life. It's very difficult, but it gets the point across. Finally, putting in hard particles again stops dislocations. If you've got an aluminium bicycle frame, it'll be hardened in that way. Remember lithium, 0.53, put in 4% in aluminium, density goes down by 12, and it gets stronger. Is this a sexy alloy? No, it's the serial number of my rally drifter. And somebody stole it in 1982, yeah? So if you're on YouTube and you know what it is, I want it back. Further reading, watch this film. James Stewart, Marlene Dietrich. It's a tale of love and passion and metal fatigue of this complex wing. That's him doing the testing, and I've modelled him myself on that person. Yeah? Right, Paris law, this is an equation that gives you fatigue crack growth rate against stress intensity. Put it into Google, what do you get? Paris Hilton leaving the courts with a lawyer. That's the sign of the times. So I'll be in quadrant C on Christmas morning at 9:30 for the test. Yeah? You're all going to be there. You don't need any calculators. Just bring a rug, caterpillar, corner of the cob, and a snooker cue, and you'll be fine. Yeah? Thank you.